Hi, my name is Jon Hsieh. I'm a product manager here at BigEye. And today I'm going to talk about what is so modern about the modern data stack. This is a term that's been around for the past year or two, and it had a lot of hype. And I kind of want to give my take on it and what I think it really is about, and why I think it's important moving forward, and about why I think what trends we're going to see in data moving forward because of this. All right. So again, thank you for joining. This will be available for replay, and there is a Q&A in the interface if you wanted to ask questions that I can try to answer at the end. All right. So let's just jump into it. So who am I? I'm Jon Hsieh. I am a product manager responsible for the alert to resolution phase of BigEye, a data observability platform. Basically, once a problem shows up, once we detect a problem with your data, I'm kind of responsible for everything after that. Before my role at BigEye, I was at Cloudera for many years. I'd been the PM for data governance, responsible for lineage, responsible for data access controls, and responsible for kind of data engineering pipeline related things. Before that, I was a principal engineer, responsible for our DevOps infrastructure and some of our data engineering infrastructure. And before that, I was a heavy contributor to the big data systems that were very popular 10 years ago, an Apache Software Foundation member, pretty hardcore engineering back in the day. But these days, I think it's all about the data, right? So what's the story I'm going to tell? Well, I think the modern data stack is really a story about the evolution of data systems, the de-evolution that has happened in the past couple of years around the stack, the coevolution with other ways of doing work, software perhaps, and then this revolution that's going to come because of all these different changes that have come along the way. So I'm going to hop in and kind of focus on the slides more, but please feel free to ask questions and I'll try to answer them at the end. So evolution, right? Modern data stack. What is the definition of modern? Well, I think modern is always kind of a reaction. So what is today, what is modern today is a reaction to what was classical, what was there in the past. So in the physical architecture world, you have Roman architecture, very iconic. This is the way it's been done for hundreds or thousands of years. And we see this even in modern buildings today, right? Or maybe the pyramids. These are large, centrally managed kind of buildings and architectures that require powerful organizations or powerful people in order to build. They take a lot of time and planning. They're very expensive, and only the most important things, our pharaohs or our emperors could really build these things and use these things. There are reactions in the world of architecture. This is an example of brutalist architecture. And in this reaction phase, we go to very extreme versions or very extreme designs. Here, this is about as Spartan as you can get, concrete, no decoration. And that's kind of one example. Another example is in the other direction. We have expressivism. We have extremely organic and wild architecture here. This is the Sagrada Familia in Barcelona. But as we make progress, as we move forward, we get to today. And I think one of the properties about things that are modern today is it's a mishmash. It is a mashup of the past, some classical designs. So this is the Pittsburgh plate glass building. It is a modern looking skyscraper, but it looks like a medieval castle. And this is the CSAIL building, the MIT computer science building. And it's a mix of that expressivist, very wild kind of architecture with a pretty boring and staid, standard looking building mashed together to get you something new and something interesting. Okay, so why am I spending all this time talking about architecture? Well, I think data has gone through a similar kind of thing as well. So you have your classical data, right? That's an IBM 360 mainframe. That is about as classic as you can get. And then a little bit more recently, you had data warehousing like Teradata's and Netezza, and you use techniques like the Data Vault or Inman style or Ralph Kimball's data warehousing Bible, to organize your data. Just like the pyramids, just like the Roman buildings, these require centralized and very powerful organizations to set up and control, because it's really expensive to do. It takes a long time to design and build, even just the data model and what goes into it. And frankly, what ends up being stored there is only the most important data that your organizations have. In the past 10, 20 years, there have been a lot of reactions. So we have the brutalism that is Hadoop, right? Like this really low level clustering system that lets you store and process massive amounts of data. It's pretty rough. So believe me, I've lived there for my previous life. And then we also have this kind of more expressive world. We have graph databases and NoSQL databases like Neo4j and MongoDB. We've kind of pushed in different directions to solve different problems and specialized to handle those kinds of things. And then I like to use Amazon S3 as an example also. This is kind of like the minimalist design. It's a very simple get put kind of thing, but it tackles this scaling problem and the storage problem very elegantly and in a way that can scale to massive amounts of data. Over time, we've started to get the more modern architectures and the more postmodern architectures, right? So we have Redshift, which is kind of a combination of the look and feel of a data warehouse, but on top of the cloud, right? Or we have Databricks, which is kind of the look and feel of S3 and Hadoop, but moving more and more towards a programmatic model and eventually more of a SQL model for processing your data. And then finally, where we are today with things like Snowflake, BigQuery, Azure Synapse, and Trino, these things look and feel like a traditional database, like a traditional data warehouse, but they're built upon these more extreme reactions in the data architecture space. So this is really talking about the core of the modern data stack, the data warehouse, the database that's used to store and query the data. Around that has been built an ecosystem called the modern data stack. Now, this is a term that's been popularized in 2020, 2021. It was a great way to kind of figure out where you are as a company or what your needs are. And they're kind of focused on different aspects of getting data in and out or using the data around the data warehouse. It was also a great way to get funding back in 2020 and 2021. At the core is the cloud data warehouse. And around it, you have data integration tools that help you pull in data into the data warehouse as a service, right? We have data transformation services like dbt. You can also put Databricks in there too, right? Different ways of processing and data and converting it into something more valuable. You have data analytics, ways of visualizing it and sharing that information and presenting it to more business level people. Metric stores are kind of an extension of that. And then finally, you have as a input-output system, a reverse ETL system. I like the term data activation. That's kind of a new version of it, but it's putting the data that you've processed back out to the end systems. If you have salespeople who use HubSpot or Salesforce, it's really great if you do all this processing and push it back out to those platforms because that's what they're going to use on a day-to-day basis. So it's really taking all this back-end stuff and making it front and center again for your data consumers and your data users. Surrounding all this, you have data governance and you have data catalogs to help you find the data and data observability to help you ensure quality around your data. And then last of all, you have data orchestration. This is the set of tools that help you kind of coordinate all these different services from an operational perspective. Right. So I like the big boxes here. I like the diagram that our friends at Continuum have put together. It is really talking about these different functional components that make up a modern data stack. It's kind of this mix and match ability to choose the best of breed for you and your use cases. But really what the modern data stack has become is it's become more of a marketing term, right? So this ecosystem has grown and every company has their own version of this diagram. There are even podcasts and blogs and newsletters all about this stuff, right? So the term itself has taken on a lot of hype, frankly. And that hype, I think, has led to a de-evolution and a more desperate and different ways of splitting up the stack and kind of more pieces to that. Everybody wanted to be kind of part of it, and each of these individual pieces take one of these extreme design choices or focus solely on one of the components, one of those functions, and really try to nail it, really try to go very extreme with it. We end up with a picture like this. This is Matt Turk's MAD stack or modern data and AI stack. And frankly, this is an eye chart. There are so many different categories and many companies in all these places. Just the heterogeneity that you have to deal with sort of has become impossible, frankly. And this is last year's. He hasn't come up with a new version of it yet, but many things, many categories here. This hype has its reactions, right? So, there's the mythical modern data stack. Is the modern data stack dead? or drop the modern data stack. I like that little database humor right there. So, it has had this kind of blowback, and this heterogeneity is a problem that is kind of the Achilles heel of this stack. But I think underneath of it, there really is this coevolution going on, and we're mimicking a different domain, or one that a lot of people think is a different domain, but I think is actually quite similar. So let me talk about how and what trends I think the data stack and the modern data stack will follow and kind of move towards and co-evolve with. So let me take a step back. Modern architectures and postmodern architectures, these are mashups. These are combinations of classical ideas, known, proven ideas, with kind of these extreme designs and these new hyper-focused things. And you get to recombine things that have been deconstructed. That stack picture is heavily deconstructed. And now you pull these pieces back together and you create something that's new, novel, and probably more useful than existed before, and enables a whole bunch of new things to happen. So that's what's got me excited about this area. My claim is that data engineering is evolving. This coevolution is borrowing from lots of ideas from software engineering. Not a new idea, but one I think is very powerful and kind of leads us to a bunch of different conclusions and things that we can think about what's going to happen moving forward. Software engineering in the 2000s, the advent of the cloud allowed you to spin up machines very quickly, made infrastructure easy, and the rise of the cloud data warehouse allowed you to get cloud data warehouse infrastructure quickly and relatively cheaply. Didn't require the 2 quarters of lead up to build out a cluster, or to pay a large upfront in order to get the hardware in place to do these kinds of things. What used to take months now can take a couple minutes or maybe an afternoon. Deployment automation. Hey, a lot of the DevOps things around like Chef and Puppet and Terraform and all these different mechanisms for you to automatically deploy virtual resources in the cloud have really enabled kind of a large explosion of things that you can do, and opened up who can actually do software services infrastructure. I think the ETL platforms that we have today that have been growing kind of fill that same niche. Now, data engineering is something that you can do, and there's lots of different ways to do it as well. The most recent and biggest kind of development around services in the software world is monitoring and observability. Think Datadog. And I think that data reliability, kind of the analog to monitoring and observability for your services, data reliability focused on your data pipelines, and more importantly, the data itself, is this kind of next logical step in the evolution of the data stack. And there are reasons why this is really important. So let's start off with a quick example. Here is a simple data pipeline, and you have different players involved with it. First, you need to collect that data, then you need to enrich it with some ETL, then you want to generally create some reports or maybe build some ML models and predict some things from it. Now, this could all be one person, your full stack data engineer, or it could be broken up into different types of data engineers, maybe a data ingest engineer, a data ops engineer, a data engineer, a data analyst, or a data scientist, right? So, there's different roles and different specialties to data engineering, but the concept of a full stack data engineer does and should exist, just like a full stack software engineer. Now, this gets more interesting. Like in software, we build services, we build things, and we connect them together, and you have this interconnectedness, right? And that's something that's really important about data. When you interconnect data, you merge data or join data with one source to another, you're actually able to create new insights. You're actually able to ask new questions and get specific answers for them. And that's extremely powerful. And let me give a kind of more concrete example. This was a data pipeline that I built in a previous life. I'm collecting data from Amazon, I'm collecting data from Google, I'm collecting data from Azure, and I'm collecting data from our internal systems. And through combinations of Spark jobs, Scoop jobs, Python code, SQL code, I'm engineering a new data set that allows me to, a data model that allows me to query how people have been spending their cloud resources. And it's a large bit of data engineering to make that pipeline go through and be reliable. So these things just get more and more complicated, but you also get into this world where if this thing were to scale up, you might have, different sets of people or different teams of people responsible for different subsets of the overall data pipeline. So one observation that I've made is that there's many different types of data engineers. There are data engineers who used to be software engineers. There are data engineers who used to be ETL engineers. And there's data engineers today, which we call analytics engineers, that do things using SQL. So let's dive into each of these, because I think the question here is like, hey, what's the right way to do it? Data engineering, when it's done by software engineers, tends to want to follow a software development-like process. They want to have a software development lifecycle. One key piece of DevOps in the software world is a CI/CD process, a continuous integration, continuous deployment process that allows them to be agile with confidence when they're building their software. And if you squint, there's this really great analogy between software artifacts and software processes and data engineering processes and data engineering artifacts. A data asset or a data set is like a library or a service that's out there. A schema of a database or a schema of a table is like an API for REST API or a GraphQL API. Your build system and your compilers are sort of like your pipelines and your workflows. Lineage is essentially the same thing as dependency management. This service depends on this service, or this library depends on that library. This data set depended on this other data set. And along with these kind of artifacts, there's also a need, I think, to bring some of the processes from software into data engineering. Code review, dev and prod branches, testing, operations, DevOps or data ops. And I think the key of it is a new discipline around data reliability engineering, similar to what has evolved at what we call site reliability engineering today. Now, that's not the only way to do it. Some engineers come from a traditional ETL background, and they're used to using graphical tools to draw their pipelines and test and pipelines and have processes and how these things get changed over time. This really kind of opens up the audience of who can do data engineering because it's simplified and doesn't require code or is low code. Now here I have 4 different products out there, and frankly, they look pretty much the same, right? Like Informatica, Talend, Matillion, NiFi, they all have this kind of drag and drop interface where you connect pieces together, data flows through it, and now you have created a data engineering pipeline of some sort. So this is actually a pretty large industry, a large business, and in the NASCAR slide, there are the most of these out there, and there's a bunch of new ones as well. We have things from the classical age, like your Talends and Informatica. We have something from the reaction age, StreamSets and NiFi, and here are some of the newer ones: Matillion, Prophecy, Azure Synapse Studio. I think the newest entry into this world is the analytics engineer, data engineering done by analytics engineers, or frankly, these used to be data analysts. Here, the data engineering is all done via SQL directly on the data warehouse. So instead of having to have pristine data land in the data warehouse, we throw more raw data in and assume that we're going to refine that data. And that's kind of the process we use here. dbt is the prime example here. And really what we're trying to do is we're trying to enable this broader set of people who can write SQL queries, and give them the basics to be able to start creating their own data pipelines. Nice things about this is that it's compatible with the software development lifecycle, wanting to do CI/CD for your data pipelines. It leverages your existing SQL skill sets, and it does it by adding variables in places so that you can actually have a production version of your data, but test it in a dev version of it without impacting everybody else. So some really nice properties that you can pick up borrowed from software engineering, but at a much simpler level that more people can actually work at. Now you'll notice here there's a little star. One of the things in the software world is that you need testing in order to make sure that something is promotable. And I think that's one of the pieces that is critical in this kind of world moving forward. Okay, so I sort of hinted at it. What is the right way to do data engineering, right? I think everybody has an opinion here of which way is the true way and the correct way to do it. I think this is a trick question. I think the most important thing here is to focus on the data more than the tools. In the software world, there are many ways to write software, different kinds of software, different kinds of stacks that you use. in order to build different kinds of software. And I think that is exactly the same case here in the data engineering world as well. What we really need to focus on is the data. And we want these properties, like being able to test things, being able to have repeatable processes, being able to roll back, being able to, work agilely with confidence when we're making new data pipelines or changes to them. And I truly believe all of these approaches are valid, and you need to be in a world where all of these can work together. Now, if you have different kinds of people using different kinds of tools, one conclusion is that, hey, data engineering at the end of the day is a team sport. You need different types of people specialized in different areas. You might start off with a full stack data engineer who's kind of responsible for all the levels in the data science hierarchy of needs, from the collection to the moving and storage, the processing and cleaning and prep, to the segmentation, to the testing, and to the deep learning and AI. But as your organization grows, this stratifies, right? And you need different players and different types of people to work together. Now, I claim that the two bottom layers have been sort of solved by our cloud data warehouses. It's darn easy to set up one of these things these days. Credit card, swipe, afternoon, good to go. Everybody wants to try to get to these AI and deep learning things, but really for that to be enabled, the most sophisticated data organizations that can do this have a lot of infrastructure around cleaning, anomaly detection, prep, and how we manage and model and organize the data. And again, like, I think all these different tools that you can use are important, but at the end of the day, in this middle level, it becomes the data. The data becomes your focus. So what are these different roles? Well, we have the data ingest people, we have the data engineers, we have the warehousing people, and the data science people. And today, these worlds overlap quite a bit, right? A data engineer might do a little bit of everything. The data warehousing person might do a little bit of the data engineering and data science. This is just the reality of the world we're in right now. It's very fluid, and people have different skill sets, but they need to come together and work together. Let me kind of be, a little bit of an abstract, more complicated example. We might have multiple teams of people working together. The gray team does some ingest. The red team does some ingest and connects to the gray data. The purple team does some ingest. The yellow team does some ingest. The blue team, uses the purple, red, and yellow data, and transitively uses the gray data. And then we have a data science team creating a function from the data, effectively a predictor that's using the blue team and the yellow team's data. So it is this web of interconnected roles and people that really say, hey, we need contracts where these different teams are interfacing, so that the red team can believe and trust the data coming from the gray team, or the data scientists can trust the data coming from the yellow and blue teams, right? So as we have more people and more teams working on this, the data becomes interconnected, and you need these guarantees, you need these contracts in place. You kind of need to treat the data as a product. And if you can do that, you can have agility and confidence with the changes that you make at the bottom of the stack, in the middle of the stack, and at the top of the stack. At the end of the day, this move and this push towards more confidence and more agility with your data pipelines away from the siloed world and a more interconnected world, I think is one of these secular trends with data. One of these things that we'll continue to see. And I think companies and tools that help this are going to be successful moving forward. Taking a step back, really what I'm arguing for is that data engineering today in the modern data stack is more like a refinery as opposed to a factory. In a factory, you're trying to take raw materials and create the perfect widget at the end of the day. And I don't think that's really possible. I think the goal is to refine and improve the yield and to get things that are purer or better or more trustable, but getting to absolutely perfect is kind of a Sisyphean task, right? And this kind of mentality kind of leads to where I think we're going to go next. The revolution, right? So I talked about evolution. We talked about how classical and the reactions and the modern day is kind of a mishmash. De-evolution, the deconstruction of the different parts of a data stack. The coevolution, how we're borrowing ideas from software. And finally, I think, where are we headed because of these, trends in the data world? I think it's a revolution, and I think the revolution is going to be focused on the site reliability engineer or the data reliability engineer kind of role. So let me talk about what a site reliability engineer is, right? So this is kind of the latest level on the people side and on the data side of software development, right? So a site reliability engineer, it's a set of principles, a set of rules and practices. It's a role that a person has to ensure the scalable and highly reliable operations and deployment of infrastructure, right? And these 7 principles come from Google's SRE guide. Google has been working at scale for a very long time, but the ability to embrace risk, right? Your uptime is not going to be 100%. The ability to set standards. Well, if the uptime is not going to be 100%, I expect 3 nines or I expect 4 nines. And if it's under that threshold, that's fine, right? Reducing toil, like doing the same thing over and over, and it can get really boring. It can get really boring. Monitoring everything. You can't really improve anything unless you can monitor and measure it. Using automation, or eliminating those things that can cause, eliminating the things that mundane tasks, mistakes that can be made with mundane tasks. Control releases, the ability to roll back if a new change actually causes problems. And to favor simplicity. This is actually one that's pretty important, right? Simple systems generally are easier to scale, easier to manage. And in these interconnected things are already complex enough. Keeping things simple goes a long way. We're going to take these principles and move them over to data and data engineering and a new discipline called data reliability engineering. So we're treating the data quality and the data pipeline as if it was a software engineering project and kind of bringing these principles into it as well. You want to ensure that the data is fit for use by the people consuming it. You want it to be correct and accurate and up to date when a decision maker is trying to decide what kind of business decisions are going to affect the future of the company that you're at. Real revenue can ride on it. For AI and ML projects, it's garbage in, garbage out. If you have bad data coming in, you're going to predict bad results. And embedded in analytics. One of the things today is that changing a data pipeline can be very painful and can be very slow, and bringing that agility and confidence and reliability back into it, I think is, the critical problem to solve today. Similar ideas, embracing risk. You're not going to have perfect data. There's going to be some data that's out of spec. Setting standards. How far spec are you going to allow? Well, I'll allow 3 nines worth of non-null. I'll allow, 3 nines of data that, and a little bit of data that might have some nulls in it unexpectedly. Reducing toil. Data pipelines are notoriously hard to update. There's a lot of manual effort in there. How can we automate that? Like number 5. A key piece, a gap today, is the ability to monitor things, right? How can you monitor your data? It's not just monitoring the pipeline, it's actually monitoring the values that are in your data sets as well. Are they normal? Are they anomalous? Are they things that you expect to see? And if something is unexpected, is it something that is due to a bug or due to something that's actually a business changing thing, a metric that will change, a business outcome? And similarly, I think there's a lot of interesting things about controlling releases. Hey, if I could version my data, how do I manage slowly changing dimensions, et cetera? There's techniques out there for that. And again, favoring simplicity, only going complex if we have to. So the argument that I want to make is that data observability is one of these key things. And you have a scenario today where a VP of growth is looking at data. Maybe you guys have seen this before. And he says, hey, something is wrong. And as a data engineer, you're in this reactive state. And it takes time because there's lots of disparate systems that you need to consolidate and go through to figure out what the heck is going on. And it just takes too long. This scenario is actually wrong, right? Like we want to be in a place as a data engineer to proactively catch these problems and prevent these fire spills. I want to be able to tell the VP that, hey, don't trust the data for a little bit. Some of the data is late. If you can wait till this time, then you can actually run it. And I feel like a data observability tool like BigEye is one of these things that can help. We can proactively tell you that something is wrong before you push it to production or before the report that your CFO depends on is going to use it. So BigEye is a tool in the data observability space, the data reliability engineering space, that helps you improve the quality of your data and your data pipelines. It helps you at the operational level. Hey, is data being delivered? Is new data coming in at the volume that we expect? It helps you at the business quality level. hey, we had constraints in our old world with, SQL constraints and referential integrity. Can we bring those guarantees back into your data? And can we actually start tracking the values of your data? I use BigEye to track product metrics about BigEye itself. And that's really powerful because I can use it to tell me and send alerts when user, there's new usage on particular features or a drop in some activity that used to be at a certain level. Really what this is about enabling you to trust your data and enabling your people to trust your data, because you have the processes in place to ensure high quality, allow you to make changes agilely, and make your data something that you can rely on. So thanks for making it all the way through. The quick summary: we've had an evolution of the data stack starting from our data processing systems. At each level, we've had a Cambrian, in the most recent iteration around the cloud data warehouse, we've had a Cambrian explosion of tools around it, highly heterogeneous, lots of different things that are out there. And the way to deal with it, in my mind, is a coevolution, borrowing ideas from the software world, the already very heterogeneous software world, and focusing more on the data, focusing more on the people, and focusing on some of these engineering practices that can help you build reliable data pipelines and high quality data. I think the revolution, one of the big trends, one of the big ideas that's going to help solve this problem in this postmodern data world is focusing on data reliability engineering, bringing those practices today from an SRE world into the data engineering world. So again, what's so modern about the modern data stack? It's decentralized. It is focusing more and more on the people and the practices. And it is a world where things are changing pretty rapidly, and the ability to combine and work with these things together is an advantage for you. So anyway, thank you for joining. I hope this was interesting. I'd love to hear your feedback if you agree or disagree or think I'm, want to make some counter arguments. I'd love to interact. My name is Jon Hsieh. There's my Twitter handle. Feel free to tweet at me. And again, thank you very much. The recording will be available on YouTube. And yeah, good luck out there with your data engineering and your modern data stacks. Thank you.